LipidSuite offers interactive analysis and enrichment of clinical and experimental lipidomics. So basically, it's a step-by-step workflow. You can pre-process, explore, and basically perform differential analysis, enrichment of targeted and untargeted lipidomics of experimental and clinical operation. It offers also, as you'll see shortly in this demo, it offers the capabilities for the users to subset their data, slice the data to focus or exclude certain specific sample groups or types or lipid classes, and basically perform all the analysis on the sliced data. So if you go to suite.lipidomics.org, you'll see this screen where you can actually just watch this video tutorial from this button, or basically go to the app itself by clicking Start the Lipid Machine. If you have any bug reports or enhancements that you want to, or any feedback that you want to share with us, just click on that and we'll basically direct you to send me an email. So once you click the start button, it will take a few moments to load the app itself, where you'll get basically the first screen here, where you have the input. So it supports basically a skyline export, where you can basically directly export your transition results and import it here. You can also input a numerical matrix, which is basically any CSV file where the rows are lipids and the columns are samples. And here is an MWTAP, which is a format for metabolomics workbench as well. So this is all of these supported. You can actually download example files, so you can actually see how to construct or follow suit from these. So if you click numerical matrix, it will tell you also you can download an example file. And here also in MWTAB, you can also download an example file. So if you want to just quickly explore datasets, we included two datasets. One from an experimental setting, which is a mouse serum lipidomics, and the other one from a clinical setting, which is a breast cancer tissue lipidomics. There's a brief explanation for both datasets here. Well, and once you click load dataset, it will act as if you actually uploaded this dataset, and it will allow you to interact with it. So in this tutorial, I'll just go through the mouse serum lipidomics, which is a targeted lipidomics dataset, and this is a skyline export. And we have 4 groups of mice. They are basically fed different diets, and basically they also they drank different, basically a DCA, the deoxycholic acid, or water. And so we have basically 4 groups in this. Once we click load dataset, or you can basically download the dataset files and upload them yourself, it will give you the same results. I'll tell you this is the lipid class distribution. So this is the distribution of and the number of classes of lipids, lipid molecules belonging to each class. You can see here this is an overview of the data set. If you scroll down, this data set has 58 samples, 277 lipids in 10 classes. You can see also here there's a note that basically one molecule was not parsed correctly, so it couldn't actually infer what is the lipid class. Here we can see here this is a typo here, there's an extra P here, and it doesn't follow the format, which is class, and then XX, which is the chain length, and then YY, which is the unsaturation number and the number of double bonds. So so you can see here there's one missing here, so we can go to the lipids tab, where it will actually show us everything that was automatically extracted from the lipid name. And so here basically what we want to do is probably want to fix the molecule that was not parsed. So here, go back and see here, this is PI341P. So let's go here to lipids and try to fix that. So PI was 34.1, and I can see here there's one with a typo here. So by clicking on the molecule name here, it'll allow you to edit the name. So just removing the typo here, and then basically it's fixed. Let's go check here. It says now the note is gone, and you can see here all of them are annotated. So now that we have basically the total CL, total chain length, total CS, the chain unsaturation, and then the lipid class, which basically these annotations will be with us through the analysis and the data exploration. We can also see here the samples. So we have 4 groups of samples, as I said earlier, but we have also as well, we've included here, we've included as well QCs and blanks, so these also will be visible now when we actually go to the plotting and data exploration. So now that we've fixed the typos here in the input, we're ready to actually go and look at the QC. So we've got here, so you can either look at the sample QC or the lipid QC. So basically, it's different ways to plot your data set. So here we'll look at the total ion current, TIC, and here, because you can actually export different things from Skyline, you can actually plot anything that you want here. So we'll stick with the peak area, and we'll color basically the samples by their group annotation. It's best to actually log scale the area because they're not they're distributed in a logarithmic scale. And you can see here this is the log2 area, and these are the sample groups here. You can see here the blanks have low TIC as expected. So in all plots here, you'll see this button here, display interactive graphics, which can be turned on and off. So if it's turned off, you can basically display this as an image, and you can actually save that and put it in your publication if you want. If you want to interactively look at the plot, you can just display interactive plot, and when you hover over everything, it will actually show you what kind of sample and what kind of values are there. You can by clicking and dragging, you can actually zoom in, and by double clicking anywhere, it will actually reset and zoom out. So, so as you can see here, this is a highly interactive plot. More than that, you can actually subset your samples, your data set. So, for example, let's say that we want to actually have a look at the total ion current, but not for all lipid classes, but for a specific lipid class. So now all of them are selected. If I click deselect all, and let's say I want to focus just on PC. Phosphatidylcholine. So once I'm done with slicing my data set, I can just click plot, and what it will do, it will basically give me basically the TIC for the PC only. You can do the same also for groups. Let's say we want to focus on the diets. Let's say we want to look at the QC only, and once we click that, you'll see only the samples are colored. Only the QC samples are actually shown here. So this can be done in most plots and analysis as we go. So I've demonstrated here. There are also you can actually display box plots as well to actually look at the distribution of that, and so on and so forth. We can do the same for lipids as well. For example, so we're looking at plotting basically lipid molecules. So in this case, for example, we want to look at the percent CV of lipid molecules. It doesn't make sense to log scale here, for example. So we'll just basically look at the CV of the area, of the peak area across samples. And then, for example, if you want to exclude high molecules with high percent CV, you can do so. It makes sense actually here, for example, to just slice the samples by group and include only the QC samples. So you can see here we can actually look at the percent CV only in the QC samples. And of course, if they have high CV in the QC samples, then it will be better actually to exclude them from the subsequent analysis. So you can see here there are a few things here that came out that stood out basically, that have higher percent CV, and these can be marked and then basically removed later. Once we're happy with the QC and we actually mark which samples that we want to exclude and which samples that we want to keep, we can actually go to the summarization. Summarization is mainly basically for molecules that were measured with multiple transitions, and it applies to a limited extent in untargeted lipidomics when you measure a molecule multiple times. If you want to summarize them, then you can basically select the transition with the maximum intensity, but you can also average transitions, or you can just keep them basically keep the multiple measurements if need be. If you have missing data, then you can impute them using an array of methods here. We'll use here, for example, we'll assume that our data is missing at random. So we'll use a K9 method, and then we can actually specify the number of neighbors. If you choose other methods, there will be also relevant parameters as well to set. And also, since our data is not log transformed, this is very important to actually log transform it before we go to normalization and differential expression. So once we click the impute, we can see here it says we imputed 79 values. And we can see here as well that the values that were imputed mostly reside on the lower end here. So these are the number of values that were imputed and the total number of values. So we can see here mostly our distribution didn't change. It looks like a nearly normal distribution. We're happy with that, so we can probably go to the next step. Normalization. So mainly, by default, we use a PQN normalization. But if you have internal standards, you can, as in actually this data set has internal standards, you can actually use them, and we'll actually do a class level internal standard normalization. And then when you're normalizing, it's actually better to exclude blanks. So if automatically they're detected from the TIC. But if they're not detected, it's actually better to mark them so that they are excluded when you're doing normalization. Then basically, once you click normalize, it will actually display box plots before and after normalization. And you can see here basically the blanks were excluded in here, and in general the samples look normalized or aligned together. They have similar distributions with the exception of a few outliers, which might be actually of biological origin. Then basically we have now a pre-processed normalized data set that we're ready actually to explore and perform differential analysis on. Simple exploration can be done using PCA. First, you can actually choose the principal component that you want to actually plot as PC1 and PC2, and you can actually group also by different sample annotation. You can actually color by different sample annotations as well. And as I said before, the interactivity is optional. So if you need that for a publication, it's probably actually best to just switch off the interactivity and right-click and save this as an image. Also, if you need to do a targeted or a multivariate analysis here for a labeled supervised PCA, so OPLS-DA, you can actually you can actually choose the groups here, and you can plot the OPLS-DA as well. Similar to basically all of the steps before, we have a data subset tab here, where you can actually perform that on specific classes, or actually exclude some of the groups if you want. And then basically you can look at how this actually will change the separation between the groups. You can also look at the loading plot. So the loading plot is best viewed in a non-interactive way, where it actually displays the top molecules here. So you can see here these are the molecules that contribute most to the separation between the normal diet water and normal diet DCA, for example. If we change that to like a high-fat diet and normal diet, you can see different. Let's actually try that. So high-fat water, and let's plot that. And let's actually look at the loading plot. Just taking a few moments. And switching off the interactive plot, the interactivity, so that we can actually display the labels. And here are the labels. Here now you can see mostly it's actually the PCs and the SMs as well. This is the loading plot that basically displays which lipids were actually contributing to the separation between the high-fat diet and the normal diet. Going on to the differential analysis, so we have a univariate analysis which uses a moderated t-test implemented from the limit package widely used in gene expression as well, gene expression analysis. So here you can basically choose your two groups. If you want to do a comparison here, a two-group comparison, but you can also do a multi-group comparison, which is ANOVA, where you actually just use the grouping variable, and it will actually just use an ANOVA style differential analysis. Let's go with two groups now, so it's more likely to be relevant to most people here. So here we'll compare normal fat diet and high fat diet. You can, if you have a clinical annotation or in complex experimental designs, you may actually want to adjust by confounding factors, which is very easy here by just you click adjust by. In this simple experimental design, there's not enough complexity to allow adjustment here, so I'm not demonstrating that here. So now we have a two-group comparison. We just click perform analysis, and what it will show us a volcano plot here, where you can actually basically interactively look at it, and you can see the log FC, and they are colored by the lipid class. So you can see here it's probably mostly ceramides downregulated and PCs upregulated. So this we can actually see very quickly. You can export the results as an Excel CSV file, or just copy it and paste it somewhere else. Moving on, basically you can actually use this differential analysis to perform a lipid enrichment analysis. So we'll use the log fold change to rank all the lipids, and then we'll do an enrichment analysis on top of that. Once you click enrichment analysis here, it will actually show which classes are enriched. So you can actually see that significantly ceramides are actually downregulated. You can see here the PCs also are significantly upregulated in our case. If you want to export the raw table, it's here in Enrichment Result tab, where you can actually download it and use it or plot it your own way. There's also a chain trend analysis. So this actually looks at the chain information rather than the lipid class, and see if the regulation is correlated with a certain with a trend in the chain length or the unsaturation. So in this case, for example, we have the normal fat, the normal diet and the high fat diet basically is are correlating with high chain lengths, for example. So basically, higher chain length is getting downregulated with high fat diet. Once you're happy with that, you can actually look as well you can go to the heat map, and basically this will actually hierarchically cluster your lipids and your samples, as it will show shortly. So it takes a bit to actually load, but okay, here it is. So you can see here these are the sample annotation here, and we chose basically to show all of them here, the group and the diet and the bile acids. And you can see here these are hierarchically clustered. They're beautifully separated in this case, which is rare, I guess, in clinical settings. And then here there's the molecule, and when you actually hover over that, it will show you what molecule and what is the log2 area of that as well. You can see here which ones are actually correlated, which lipids are actually clustered together as well. You can see here a few PCs clustered together. You can see here as well, these are the PCPs and PCOs, the plasminols. So overall, you can actually export this as well as an image by clicking, I think, on the camera here. So yeah, that's it for LipidSuite. Let us know if you need any additional features, or if you have any feedback, or if you've discovered any bugs. We're happy to support it. Thanks.